Hello, this is Jack Jackson. In this video, we're going to talk about line integrals of a scalar function of three variables. In our last video, we talked about line integrals of a scalar function of two variables, and we're going to see that this generalizes nicely to higher dimensions. So, if you remember from our last video, we talked about the concept of a line integral of a scalar function of two variables. We saw that as an extension of the concept of an integral over a line segment. We just have a line segment, or an interval over the x-axis. We go up to the curve and we find an area there. That's an area of a planar figure, a fence or a wall, where the base is just a line segment and you're going straight up. Okay? We generalize that now by letting the curve no longer be restricted to the x-axis, but let it wander around an xy plane. So it's still a plane curve, but it's no longer necessarily just a line segment. Or it might be a line segment, but it's not necessarily going along the x-axis. Or, like I said, it could be even more general. It could be some curvy thing wandering around, like this part of a cosine curve here. And then the height of this is determined by some function. In this case, it's a function of the points along the curve, which have x and y coordinates. So it's a function of two variables. Find a point there and make the height. Okay, and so this idea generalizes very nicely. So again, we're going to be able to think of this as an area of a wall, but the curve that's our domain now is not necessarily even restricted to a plane, but could wander around maybe some continuous curve in space. So we have a space curve, a 3D curve. And again, we can go up from that curve and build a wall, and the height of that wall is given as some function, this time of the coordinates on the curve. So it's going to be given as a function of an x, y, and z. So a function of three variables. So let's look at an example of that. So we could give a position vector function, r of t, to define a curve, which is essentially parametric equations for the line, or for the curve, not necessarily a line. This one is a space curve. It's a spiral or helix, an elliptical one. So this is x is cosine of t, y is 3 sine of t, and z is 1/4 t. Or in other words, the r vector of t is cosine of t I, 3 sine of t j, and 1/4 t k. Okay? Or cosine of t, 3 sine of t, 1/4 t, that vector function. And we're going to let t run from 0 to 6 pi. So if you look at this, if you just had this in a plane, cosine t, 3 sine of t, that would trace out an ellipse. And by going from 0 to 6 pi, we're tracing over that ellipse 3 times. But meanwhile, the t value is increasing from 0 to 1/4 of 6 pi. And so it's rising in height. So this gives us a spiral that's going around an elliptical cylinder. Now, if we want to, the function that we're going to be integrating is 1/10 x squared plus z. So that is, again, a formula that depends on x, y, and z, or actually y didn't really figure into it, but it figures on the points along the curve. And that gives us a height of our function. Okay. So what we're looking at here is heights above this curve are given by this formula. Well, whatever it was before, it was 1/10 x squared plus z. And if you graph that curve, going up where the heights are that much above this curve, you get a surface, okay, that ranges from 1/10 tall here to about 5/5700ths here, and we have it. So it's just a widening height as it goes along, but it follows this curve. We'll break that into little rectangles like this. Now the base of the rectangle is going to be, again, a secant line segment like it was in our last video. Delta S sub k is going to be the width of that particular part. Okay, and but this time, because we're in 3 dimensions, we have our 3-dimensional Pythagorean theorem extension, that tells us the length there is delta k squared plus delta y squared plus delta z squared, and then square root the whole thing. That's going to be delta s. So a point on the curve in the kth subcurve is going to be an x sub k, y k, z k. So just like we did in the last video, or just like we always do, we take our domain, we split it up into little pieces. In this case, our domain is a curve. It's this spiral thing going on here. We break it up into a little piece. Let's say like a little piece right in here. Okay, and somewhere within that piece, we pick an xk, yk, zk, and evaluate our function to find the height of a rectangle. Okay, and the base of that rectangle is going to have length delta sk. Okay, and so it's going to give us a little rectangle that's approximately right there. Okay, and we do that all the way up and down this curve. We get that. Now to find the height of that is f of xk, yk, zk, and multiply that height times this width, and we get the area of that. I say area; it should be a signed area, because if it's that f function is negative, then it's not really height; it's a negative of a height. So a signed area, and then add those up, and we have a Riemann sum there, which is a sum of areas of rectangles. Now as usual, we take the limit as n goes to infinity and the delta s sub k's go to 0, and that gives us our line integral of our function ds. Okay, and of course the way we're going to actually do this is to turn it from a line integral into a calculus 1 integral of a single variable by parameterizing everything. So this x, y, and z are replaced by x of t, y of t, and z of t for some parameterization. And so this gives us a function there. And then what we do is we take this ds is just, of course, dx over dt squared plus dy over dt squared plus dz over dt squared, or in other words, x prime squared plus y prime squared plus z prime squared, where those are derivatives with respect to t, square root all that, multiplied by t dt, that's the ds. Now another way to see this is take advantage of our vector notation to condense the notation here a little bit. xt, yt, zt is another way of saying just r of t, r vector of t, is that essentially gives us that point, so we can just say f of that vector, and then the ds then, if you look, is just the norm of that r prime times dt, and of course we're integrating that from our initial t to our final t. Okay, so this is just another notation for the same thing, which by this we really mean this up here. Okay, so moving on to our example. We can parameterize this curve. Actually, it was given to us in parametric form. R of t is cosine of t, comma 3 sine of t, comma 1/4 t, t going from 0 to 6 pi. And our function f of x, y, z was 1/10 x squared plus z. Now we're going to need to turn that into t's. And of course, we'll do that in just a minute. But once again, to illustrate that, here is the shape again, and we're illustrating this. We're integrating that function ds over that curve as a line integral, and it's I don't have it shaded here, but it's the area between the black and the blue curves as we go around. That height right there at the beginning is pretty small. It's just about 1/10. And it goes from that up to here, which is around 0.57. Let's take a look at that briefly here. And here is the curve again. So let's just make sure everybody gets a good visual of this in 3D as I can move it around here and make this dynamic for us. So we see that we're looking over the shape of an ellipse. So all these things are going around an elliptical cylinder. So we're basically going around that ellipse and then stretching it up vertically, so we make us a spring or a helix there. And the blue graph is the actual object, the actual spring. Okay, and then the fence that we're building, if we look at, say, a piece here, it's shading going straight up from this to a certain height there, and we're going around there. And again, that height is pretty small down down here at the bottom. Let's see if I can get in things. So right here it's really small, and it gets a little wider as it goes around, a little wider, a little wider. Maximum height of the fence is right here at the top. And we're finding the area of that curvy wall there. Okay. All right. So that's what it is. To do this out, we need to go ahead and put everything in terms of t. So again, our curve is given in terms of t. We're going to need to find ds. ds is the norm of r prime, so we're going to need to find r prime. In other words, we're going to need to find x prime, y prime, and z prime. The derivative cosine of t is negative sine of t. The derivative of 3 sine t is 3 cosine t. And the derivative of 1/4 t is 1/4. So there's your r prime vector, or your component derivatives. Okay, and then ds then is the norm of that times dt. So the norm dt, the norm, of course, is just taking this thing and squaring each part, add them up, square root. So that's taking the 3 derivatives with respect to t, squaring them, then adding them up and square root. So we take negative sine of t squared plus 3 cosine of t squared plus 1/4 square. And actually I simplified that a little bit. This is just sine square, this is 9 cosine square of t, and this is 1/16. Okay, now integrating over the curve, our t values are going to go from 0 to 6 pi. That was given. And then this part right here is our original function, which is 1/10 x squared z. But x squared, let's see what's x. Well, x is cosine of t, so this becomes cosine squared t. And z is 1/4 t. So I'm going to factor 1/4 out of here, making this 1/40th, and making this 4 cosine of square t, and then just t. So I got all my fractions in sort of one place, kind of like getting common denominator. So that right there is what I put in for f of x, y, z. Now, as usual, these are kind of nasty to find antiderivatives for, so I'm just going to use a numerical techniques on a calculator to approximate this. It turns out about 11.993480903 as far as my calculator would go. So there are lots of different applications of integrals, as we know. We've seen Cal 1 and Cal 2 and Cal 3 so far. We've seen many different applications of integrals. We're seeing this as an integral, thinking of it as an area, which we can certainly visualize it that way. But of course, x and y and z could represent different things. The f could represent different things. And of course, then that would give us different interpretations of the integral. One example would be the following. Suppose the blue thing is actually a wire. So we actually have like a physical spring here. But let's say that this wire has a variable density. Okay, so it's again the same formula for our wire. R of t equals cosine of t, comma 3 sine of t, comma 1/4 t. That identifies the path that it's going along from t equal going 0 to 6 pi. But let's say that the density is variable there. So the density is the function that we were given earlier, 1/10 x squared plus z. Then that integral that we just computed could be interpreted as the mass of that wire. So the mass would be about 11.99, say in grams. That's it. The density would need to be given in grams per centimeter, so it's a linear density. and then the x, y, and z are in, say, centimeters, some length unit. Okay. Now, we can also find the center of mass of that spring. We need the mass here, and we need these moments to find x bar, y bar, and z bar. So if you look here to find x bar, we just take the basically the mass formula, but instead of just the density, we do x times the density and do that line integral, but then divide by the mass. And so it's not too hard to just change that to x, which is replaced by cosine of t. Run that through a calculator, and you get, well, close to 0, negative point, a bunch of zeros, and 371. So slightly negative according to this, basically about 0. For y prime or y bar, you do y times the density, integrate that line integral ds, divide by the mass. So there's 1 over the mass there. That's the integral we set up. It's just like before. The only difference is we're putting this part here by 3 sine t. So that's going to be in addition to the factors that we have up here for the mass. Or in place of the x, the cosine t here, it's now 3 sine t. Run that through the calculator, we get about negative 0.215818, etc. Okay, and similarly to find z bar, it's a z here instead. Z was 1/4 t. Run that through a calculator, got about 2.984. So x bar, y bar, z bar is approximately 0.000, negative 0.216, and then positive 2.984. That's to 3 decimal places, rounded off. The length of the wire, the arc length, is just found by integrating ds. In other words, integrating the function 1 ds. Again, our ds from before was this right here. And if we integrate that, again, I did it on the calculator, it's about 40.4. So there's a couple of examples. Mass, center of mass, length of the arc length. But we can also visualize this as an area. And so that is a line integral of a scalar function. We did it last video over a scalar function of 2 variables. Here we could do a scalar function of 3 variables. It would generalize nicely to even higher dimensions as well. We would just add another derivative squared under here for the inside there for the 4th variable. And of course your function of 4 variables has to be all put in terms of t to go in the front here and so forth. So you could generalize this to even higher dimensions if you wanted to.